Yesterday we have discussed about the complete generator data sheets. Okay, so um, P maximum and P minimum values, as well as Q maximum and Q minimum values, how we are going to calculate, right? And MVA base and impedance values, correct? So here we just concentrating on the main parameters called Q values, as well as how we are going to control the Q values with the help of this scheduled voltage. Okay, this is a very important parameter that we need to taking care and of an inverter of the generator. Okay, so today we are going to discuss about the transformer modeling, especially on the two winding transformer, and in continuation with the three winding as well. How we are going to do that? Let us take an example of this. Okay, just give me a second. I will take an this is an and transformer data sheet do I have. Okay, I'm just only one thing which I have take it. If you are facing still a lot of issues in my voices, kindly let me know. If it is not too much of comfortable for you, we will put it on
No,
hold
it
for
is
five
fine,
minutes
sir.
It's fine, right?
Right
Okay,
now, it
it's
is
fine. If
fine,
it's
sir.
fine, then fine.
Yes,
Okay.
sir.
If it is
Sir.
not comfortable too much, let me know. I will put it on hold for 5 to 10 minutes. Then once the supply can back, we can continue. That's fine. It will come back. It will come back in 5 to 10 minutes. That's it. It's due to heavy rain only. It's stopping, so it will come back. Okay. Um, so here I'm just taking an one transformer. Okay, that transformer data sheet I took here. So after that, I just wanted to take an transformer in PSSE as well. How they will going to use on that. Okay, I can take one node. Okay, I can take another node. Did not come 69, right? Yeah. So let us consider we should be on 33. I will come to this. Okay, I'm not here going to take this. I'm just concentrating on only this transformer modeling. Okay. Okay, so let us take this, what they are asking and what we are going to discuss about. Okay. Yeah. So I have a putting it two things here. This is an two winding transformer data sheet, and this is transformer data which has been requested by the PSSE. So what are the details we need to enter in the PSSE details, right? So in this data sheet we having a lot of parameters. We do have an insulation, we do have an thermal characteristics, everything we do have better. But as a power system engineer, what I which is an important segment which I need to take from the particular data sheet is majorly on 2 points. First point is an impedance value. Okay, impedance of the particular transformer, that is the only thing we need to take it. Okay, and second thing is an load losses. That is a two major important parameter I need to concentrate on modeling of two winding transformer in any kind of software. Okay, in any kind of software, if you want to perform any power system studies, I want to model the two winding transformer based on the two parameters. Okay, based on the two parameters is called, first one is an impedance of the transformer. Okay, impedance of the transformer, and then second thing is an load losses. Okay, load losses. This only I need to take it. Apart from that, whether I don't want any other thing, I don't want anything, whether this insulation level or thermal characteristics, I don't want that. Okay, if you want to go for an power system studies, okay, let's say for load flow, short circuit and all, these two things is only important. Okay, for the two winding transformer. Okay, 20, right? So then that's why I'm taking here So the impedance is equal to 8 percentage, okay, at 3.3 kVA base. That means 3.3 MVA base. That means this 8 percentage 8% impedance is calculated on the transformer winding MVA base. Okay, transformer winding MVA base. The transformer the rating of the transformer is equal to 3. Each transformer is 3.3. The total is 332. That is a SLD prosperity point of view. So, but this transformer impedance is calculated as 8 percentage with which base? At its own winding MVA base. Okay, at its own winding MVA base, that is 3.3 MVA base or 3300 kVA base. Anything is fine. Okay, in order to now we can jump onto this transformer details. So what they are asking, transformer impedance data. This transformer impedance data is specified as an R and X. That means I'm going to model this transformer with the help of R and X parameter. R means resistance, S means inductance or reactance. Okay, is L is an inductance, so X means reactance. Okay, so R and X, that's it. So if you want to calculate what is R and what is X, that's it. Your transformer modeling is almost done. It's not completely done, but almost done. Okay, now let us calculate how we are going to how we are going to calculate with the help of this transformer. Okay, there are three methods are there to calculate the R and X parameter of the two winding transformer, or two winding or three winding, any winding. But if you want to calculate R and X, there must be a two or three methods are there. First method, method one. Okay, method one, I will go with the R here. Going to calculate X here. Okay, this is in terms of per unit. This is in terms of per unit. Okay, I just want to do in per unit, correct? It's asking per unit. You can see specified R in per unit, specified X in per unit. Okay, so I can use this is an method one, direct method. I can mention as a direct method. Why I am mentioning this direct method is, nowadays most of the generated transformer is giving, okay, generator, sorry, most of the transformer details which is given here as a directly. That means you may able to find the R and X directly, which is in the transformer data sheet. Okay, for example, you can see here I have mentioned, I have highlighted the impedance is equal to 8 percentage at is 3300 kVA base, right? And see, the reactance is equal to 0.7949 percentage. That's an another is given. And resistance at 75 degrees Celsius is equal to 0.9 percentage. That means the values of R and X is directly given in the particular transformer data sheet. That is the first point, right? That means R is equal to how much? R is equal to 0.9 percentage. What is X? X is equal to 7.949 percentage. Okay, that's it. So we have found it directly with the help of the directly given by the data sheet. Suppose in some of the transformer data sheet which is not given directly, okay, most of it, but currently those who are providing a new transformer data sheets, they used to provide directly, they are giving R and X directly. But suppose in case if it is not given directly, suppose in case if R and X values are not given directly, then what are the another different methods that we do have? Okay, that's why method 2.
And if the values are given on the data sheet, sir, they will always be in per unit.
Yes, percentage means per unit only, both are same, either in percentage or per unit. They are given directly with help of the percentage only. That percentage can be considered as a per unit only. Okay, if
All
it is
right, sir.
divided by 100, it can take directly at per unit. Okay, it's given in per unit, that's it. Percentage or per unit, both are same. Okay, So because nowadays they are giving directly. That's it. So with the help of that, so you can use it directly. So now I'm just going to use method two. Method two means maybe either Z with XY ratio. I can give that Z with XY ratio. Method two. That means your Z percentage is commonly given in all the transform data sheet. Z is a common. Or either they give R and X directly, or else the second method they will give Z with Z by R. Sorry, with X by R. X by R should be given, right? With method two. Then how can I able to calculate for it? That Z is equal to 8 percentage, right? 8 percentage. Okay. Then now I don't have an X by R, but I just calculate X by R for our easy purpose. Your X divided by R. Okay. So this is the X by R. Maybe suppose let us consider your X by R is given as 8.83222. Okay. Or 8.83832. Let us consider they are giving like this. Suppose the transform data sheet should have either Z or X by R. Okay. Now I know the value of Z. I know the value of X by R. It's keep on fluctuating my power. Okay, fine. So your now let us jump on to one more equation, that is impedance triangle. So you can see here Z is equal to square root of R squared plus X squared. So from that we may able to calculate what is R. Okay, we can try to calculate what is R because we know the value of Z. Z squared is equal to R squared plus X squared. Sorry, X squared. Okay. Now take R squared out, then 1 plus X squared divided by R squared. Okay. Then R squared into 1 1 plus X divided by R the whole square. That means I'm just commonly out to the Shakespeare, right? Therefore, your Z squared is equal to this value. Now we just calculate R squared value. R squared is equal to Z squared divided by 1 1 plus X by R the whole square. Okay. Then taking a square root, you can find the R is R. Then R is equal to, I can for this alone I can put it in equation. Okay. Then R is equal to, taking a square root, then square root will get cancelled, divided by square root of 1 plus, sorry, X divided by R the whole square. Okay, like this it will come. Okay, if you taken common, if you take a square root of take a square root of both sides, okay, then r is equal to square will get cancelled, that z divided by 1 plus x square the whole square. Then we can easily find out what is an r. If you check means we will match the results easily. So your r is equal to z divided by square root of 1 plus x by r, x by the whole square, then close the bracket. Okay, minute difference is there, right? Because of that. No, it's not taking properly. Yeah, 1 plus, sorry, I was done wrong. X bar only square, right? I was done the bracket wrongly. 1 plus x by r the whole square. Okay, then right. Yeah, okay, yes. So now I can exactly match the value for now, right? So this is another method. Then what is x? So x is equal to, from the x by r. So I know already value of x by r. So x divided by r is equal to this value. So from that r into this value. So that is equal to x by r into, already we have found r. We found 0.7949 per unit. That's it. So this is another methodology. So either they have represents the value directly, or else they should have given the x by r value of the particular transformer. Okay, when if I maybe when I was working the 3 to 4 years before, at the time of 2020 2022, none of the transformer data sheets should have the directly R and X values. Okay, they have provided only the Z values and X bar values. But currently, when I was working on taking a modeling, I can able to see the transformer data sheet with Z, and directly they have given the R and X like this. Okay, nowadays, I'm just taking from 2004 and 2005 at the time. At the time, most of the transformer OEM can able to give the data sheets in that particular way. But even though I just wanted to explain you, suppose if there is details is not available, you must to uh, you must to have this kind of values, right? So now I can match with this value with an x bar as well. Now method three. Okay, we have another method. Suppose if x bar ratio is not given, then which one is helpful to calculate R and X? If I do not have direct values, if I do not have x bar values, then what else will be helpful for me? So is it with load losses? Okay, this will be helpful. Is that with load losses? Okay, uh, just 1 second. I will take another screenshot. Just give me a second, just 1 second. I will share another one. Okay, no, this good. So, how can you able to calculate for this with this values, right? That we will discuss now. How that are also going to be match the same results. Let's see how it is, how we can able to do that. So for this method three, we can have a load losses. Yes, we do have a load losses. Load losses of the particular transformer is equal to 118 point kilowatt, but the load losses has been calculated with 13.2 kVA. Where this 13.2 kVA comes from? That means four transformers can able to combine together. That's it. That is this four for example, one transformer rating is equal to 3.3 MVA. Okay, then if it is 4, 4 is equal to 4 transformers, that is 4 into this value, sorry, yeah, 13.2. So that's why 13.2 MVA, or else in terms of kVA means 132 100 kVA. Okay, both are same, that's why they are giving that. So they have calculated the load losses. Okay, they have calculated the load losses with the 4 transformers, combining of 4 transformers for this particular SLD. So they have given in 30 for 13,200 kVA. Okay, so then your kVA of the at the particular load losses is equal to 13,200. Okay, kVA in terms of MVA means 13.2, sorry, 13.2 MVA. Okay, and then your load losses is equal to 118 point, sorry, 118 point, how much, 118.8 kilowatt.
Sir, if we talk about one of the grid station, in grid station we have a power transformer. This means that when you are talking about this 13 MVA, this means that one transformer capacity is 13 MVA.
No, it's no, this is not one transformer's rating of 13 MVA, but it's uh yeah, maybe I will show them another SLD maybe for a better understanding. Just wait. Mm. So here, could you able to see here now? This is the one that is there. Okay, see that the inverter rating is 3.3 into 4, totally 13.2. So they have considered the two transformers winding, three winding transformer. This three transformers winding rating is 13.2. That is 13,200 kV rating. kV rating. Okay, 13,200 into 4 by 4 into 3,300 kVA. Both are same only. So either we will go with an 4 3.3 kVA. So the total transformer rating is 13.2 only. Okay, if you can
All
understand
right,
from this SLD now.
all right, sir. All right, sir.
Mm. Both are same only. For this transformer data sheets only, I took it there. Okay, the same transformer data sheet here. So this is it. Both are same. Yeah, kilowatt. Okay, so your R is equal to total load losses in, sorry, formula total load losses in megawatt divided by total MVA. Okay, therefore your R is equal to 118 in megawatt, right? So then into 10 to the power of minus 3, 10 to the power of minus 3 divided by, you can put a bracket here, divided by total MVA, 13.2 MVA. See, again I get an exact R. So R is equal to 0.009. I can validate it, right? Then again, how can I able to calculate X? Easy, right? Tell me, how can you able to proceed with X now? I know value of R for this method 3 alone. For this method 3 alone, I know the value of R. Then how can I able to calculate X? Okay,
Z is
so
equal to X
Sir,
prime.
yeah,
we have a value of Z, we have a value
yeah,
of
that's it. Simple.
X,
We have a
then we
value of
can
Z.
find a R.
Z is equal to 8%, right? 8%.
Yes, sir.
So I know the value of Z here. Then I know the value of R. Then easily we can calculate X. X is equal to square root of Z squared minus R squared. I can get the value easily. That's it. Simple methodologies. So In this three ways we can able to proceed any methodology you can able to proceed. But as of the conclusion, what I trying to explain, if you want to calculate r and x, either we need r and x value directly, or else we need an z value or z value and x by r value, or we need z value or visit value and load loss values. So without these three inputs, we can't able to calculate R and X values at any time. That's not possible. So if you want to modeling a two-winding transformer, you must to ask the particular OEM of the particular transformer. Without this data, you can't able to calculate R and X values. Why? Because I need an R and value, because without R and S value, your transfer modeling is not completed in any kind of software. Okay, so what is the conclusion of the modeling is that, okay, conclusion of the modeling, first point, we need a direct value of we need an R and X values, R and X values. For that, either Z and X by R, or Z and load loss, load loss. Without this value, we can't able to proceed further for the completion of the modeling. Okay, this is a major conclusion of this particular modeling of the transformer, right? This is first point. Second point, second point, we have to be able to note Z is calculated as per the winding MVA base. How can you able to say? Because you can go see here, impedance, first line LV to HV 8 percentage at 3300 kVA base. That is the transformer base. Okay, transformer base, that is transformer MVA base. Okay, this is we need to calculate. This is calculator as per the data sheet. Okay, refer data sheet. Data sheet. Right. Then third point, tap changing, tappings. Okay, now we need to enter the tap, we need for the tap as well, right? Then that will come to the next point. Okay, so for that I can jump onto the PSSE now. We will discuss about this line data one. How can it is mentioning? Because it is connected to the bus number 1 to bus number 2, right? And then branch 1 I already mentioned, in between the particular node, how many modeling, how many transformers are there, it will are added automatically. And from bus number 2 to automatically updated, you can mention maybe this is a two winding transformer, twin transformer. Maybe let us consider dy and 11. It is also given in the transformer. Now I just taking as a dy and 11 now, right? Yeah, now we can coming to this very important segment of input output data. What is this means, what I need to give it here? Okay, we need to follow the majorly an impedance input output code. Okay, now I already told, we will come one by one. This is on base kV or winding voltage. Okay, you can choose a winding voltage. If you choose a winding voltage, nothing important. First one is based on your per unit value. That means, see here, this is mentioning in per unit. This is, that is winding 1 in per unit, winding 2 in per unit. Suppose did you want, I don't want to reference in per unit. If you want to go for the kV means, you can go for the kV. That's simple. You can change the kV. See, 0.69 kV, 33 kV, anything is fine, anything is fine. So winding input output code should be on either 1 or 2, but I would like to suggest you to keep it on code number 2. Okay, that will be more better. And then second thing, impedance. I just wanted to recollect you, right? Okay. So that means we already calculated our impedance, right? How we are calculating impedance? We have taken the impedance from the data sheet. The data sheet is given 8 percentage at 3.3 MVA base, that is 3300 kVA base. That 3000 kVA base is a transformer MVA base. That means it's a winding MVA base. Okay, Z per unit has been calculated with a winding KVA as well as winding MVA. Is this a system MVA? No, it is not system MVA. It is given in transformer MVA base. Transformer MVA base, that is winding MVA base. So we have to select a trans winding MVA base. If it is given you wrong, your total system will be get wrong. Okay, your because internally it will calculate and transform with an MVA base. So if you're giving a system MVA base, it is wrong. Okay, it is wrong, completely wrong. Your analysis, your output will be everything should be wrong. Okay, please make a note. And this is fine. This is you can this is for our understanding purpose. You can keep it as one as this admittance we are not calculating. So your code must be okay. Your code of an input transfer transform must be okay. Here this code must be 2 to 1. Okay, code is equal to 2 to 1. Okay, this is an important. Oh, like this. Okay, 2, 2, 1. You can mention like this. Okay, code must be. This is very important. If you wrongly if you calculate it as an 2 1 1, it's wrong. Okay, it's wrong. Second code must be first and third. It doesn't matter. So it will not impact at any cost of time, but your impedance or input output code will be impacted heavily on the transformer impedance. What is an R? R is equal to 0.009 and X is equal to 0.07949. Okay, this is the value calculated. Currently, you can neglect this one. I'm not calculating any impedances and all, so this and all will not impact anything. Currently, I just neglecting this parameters and all. We will discuss when the studies will comes. And what is this? This is a nominal value. Nominal value for reference 0.69. Same you can mention. 33 you can mention. Okay. At which MVA base we are using? 13.2. Correct? 13.2 MVA base we are using. Correct? So I just used the same value. Right. And then what is this rating? Rating is equal to same. You can put 13.2 here directly. And this is as rate 2. Rate 1, rate 2, rate 3. How we can able to enter? Rate 1. Rate 1 is equal to same as transformer rating. Same as transformer rating. I think I quite running out of charge. I can try to finish it as soon as possible. Rate 2 is equal to 1.1 times of the rate 1. Okay. What is rate 3? Rate 3 is equal to 1.2 times of rate 1. Okay. This is how we need to calculate. What does this mean? What is this rate 1, rate 2, rate 3? It's quite weird. Yes, where it will be helpful means when you go for the contingency analysis or when you go for the feasibility studies, whether rate 2 is a kind of quite emergency, if there is any one parallel. When we go for the contingency analysis, right? At the time I will discuss about this, right? Uh, 13.2 here, right? Then that is equal to 1.1 into 13.2, right? That is equal to then 1.2 into 13.2, correct? Then 14.5 to copy and paste it here. Good. Then 15.4, copy and paste it here. What is rate 4, rate 5, rate 6? Yes, do we have? But uh, for currently we don't have anything. So if we don't have anything, we can give. But most probably they will give by the particular client or something. So we can take it from them. Okay. So line data is clear. Input output data is clear. Impedance data is clear. This transfer is also clear. I will let you know what is this and what is this now currently. And this control data. What is this control data? This control data is nothing but your tap changer. Okay, this is used as a tap changing. So we need to give a tap changing. Now I'm just going to give a tap changing here. So maybe let us consider tap changing is equal to voltage per unit voltage. Click OK. And then usually tap if the transformer should have a tap means the tap is on applicable on the higher side, it can able to control the lower side. Then where is the which is on the lower side? Higher side is an connected to the 101. Lower side is an 0.69 that is connected to the 1. So I'm just going to control the bus number 1 here. Okay. First point. Okay. Hope your point is clear. Then now let us consider we having a 17 tabs. Okay. 17 tabs. I just taken taking an in this transformer data sheet, we do not have an OLTC. So this particular transformer data sheet is a fixed trap. We do not have any OLTC of the particular transformer which I have showed the data because it's a inverted duty transformer. So it does not have this particular transformer does not have any OLTC of the transformer. That's why we do not have a transformer on this. Okay, but if I want to do that means what are the things I need to concentrate on this means just give an if it is a fixed tap you should not go for this auto adjust. That's it. If it is an OLTC then you have to go for auto adjust. So your auto adjust is helpful. Okay, control it. I can take it separately. Control data alone. That's it. My charging is about to shut down, so still the power is not coming. I try to complete it as little bit fast. Okay, if there is anything shut down, then we'll continue tomorrow. So then your auto adjust is for only OLTC. Disable disable it. Disable the auto adjust if the transformer have a fixed tap. Okay. Okay, good. So then we need to calculate the V maximum, V minimum. So V maximum is equal to, and how can I able to calculate? V minimum is equal to. Suppose if you having a step size, I do have a transfer data for another next 3 unit transformer I do have. At the time I will tell you how we can able to given for that. So your step size, suppose let us consider your step size is equal to 1.25 percentage. Okay, that means your V maximum is equal to 1 plus this value. Why it is coming like this? 1.25 percentage. 0. Gentle value. Ah, that's it. That is equal to 1 plus V maximum should be this value. V minimum is equal to 1 minus this value. Sorry.
Sir, what is step size?
Mm-hmm.
What is
Sorry,
step
sorry, come
size, sir?
again. Huh?
Step size.
Uh, Step size means suppose from nominal value, suppose if I want to adjust the transformer tap means at which step I need to go ahead, right? Suppose from one per unit to another I need to one step ahead means at which step I need to step, one step or two step or three step, right? For each step, for from nominal to for example from nominal to I need to in order to maintain the voltage at all the buses, then I need to increase one more step. If you increase the one more step means your step is 1.25 percentage. That means 1 plus 1.25 percentage. If you have to increase, suppose if you want to decrease means from 1 per unit to you need to decrease 1.25 percentage of the step. Uh, you got it right. If you want to adjust the tap, right? If you want to adjust tap, I need to either increasing or decreasing to
All
maintain the
right, sir.
nominal
All
voltage.
right.
Hmm.
All right, sir. This means that if we are
Hmm.
changing the tap position of the transformer,
Ah.
this will change by 1.25% of the nominal voltage.
Got it. That's good. Super. Yeah. So that
Thank
V
you, sir.
maximum V minimum you should give. Suppose then your tap should be operate at this point 1.0125. Your V minimum is equal to 0.9875. The tap should operate at this point. Once the V maximum reaching this position, your tap will be operating. That means if I increase the one step bucket means the automatically the voltage will be maintaining here. So at this time the 33 percentage or 33 into, so the nominal voltage, suppose if I apply the tap of this one step ahead, then that is equal to 33 into this point, right? This per unit, 34.4125. So copy then the tap will be nominating here. That's it. So nominal voltage is this time, but the tap is applied as the 33.4125. That means tap is applied on one step ahead, 1.025, in order to maintain the lower voltage side to be a nominal voltage, in order not to increase or decrease, to maintain 1 parent or less than 1 parent. You got it right. So it will automatically shown here. Okay, you got it right. Or else if you go for 1 parent, it will go here. I can go for per unit, right? Per unit means, see, 1.0125 it will mention here. That's it. So that is how it will be applied. So what is a tap is applied? The tap voltage should be mentioning here. This is nominal voltage, but this is tap applied voltage. That's the difference should be mentioning here. That's it. You got it right. Maybe for better understanding, I can show here. Okay, I can show here. So here in this 3-1 transformer data sheet, tomorrow we will discuss in detail of this. Okay, I just wanted to complete it right now, but still I'm just running out of charge. 30% is remaining. So see here, if there is here, so you can see here percentage step size is 1.25 percentage. What is the principal tap? Everything in detailing will give it here. That we will calculate it by tomorrow. Okay, in detailing. Yeah, but why I not mentioning here means because this transformer is an fixed tap. That's why the data sheet is fixed tap. Because of that, we do not have an options to do that. Okay, do not have an options to show it here. But in the three-winding transformer data sheet, this is a three-winding transformer. 120 bar 120 bar 1 as a three winding 66 33 22 kV side, that we will discuss it tomorrow. So if you want to, this V maximum and V minimum is a very important, and it should be there. Suppose if you're keeping 1.1 here, your tap is not applied until your voltage should reach at 1.1. Okay, when the tap will apply, my tap will apply automatically 1.0125 if it is reached. If it's reached to 1.025, it will automatically apply. Suppose if you do not have reached means, then the tap will not apply. So the V maximum and the V minimum which you want to given is a very important point that we need to take care of it. Okay, that we will discuss a little bit more in detail with the tomorrow's class for the three winding transformer. So up to this, what is the major conclusion we need to take care of it is this winding MBA is a very important when you take care of it. First point, and why means here. Why means because we are giving a winding MBA base. This winding MBA base we need to give because we have calculated this Z and X should be on. Yeah. See here 0.07 triple line. We have got exactly. You can see third. If you go for third, it should come. So 0.08% is Z and 118.8 kV. Exactly it came. See, that's it. It can automatically calculate it. I never give any values of 1.11.8, right? 118.8 in terms of watts they are giving, but we are mentioning in kilowatt, right? Kilowatt means divided by 1000, then 11.8 kilowatt it should come. But in terms of watts, it should be there. But see, only R and X values. First one is system MVA base. We should not go for the system MVA base. Why? Because your Z is calculated on a winding MVA base. So I will give a winding MVA base here. So what is the mention of third? Third is mentioning to showcase the what is an Z and X. Whether we have matching the results. Yes, we are matching the results. 0.08 percentage of Z we have calculated. Yes, that's correct. And what is the watts we have load loss we have calculated? Load loss is equal to 118.8. For the better understanding, you can see here 118.8 kilowatt. So I have matches the values correctly as per the data sheet. So our model is perfectly correct. Perfectly correct. Okay. That's it. So suppose I just wanted to tell you this either directly we need to give, or is it with the XY ratio we need to go, or is it with the load losses we need to go. This is a very important point. Okay. So far it's clear. Any doubts? I hope the doubt will not come. I have double confident on my teaching. I have seriously, I have double confident on that my explanation. Mm, So if you have any doubts, we will discuss it. That's fine. Even if it's a very basic doubts, we can discuss it. That's nothing to worry about it. And
Normally we go with the speed of sound, but today we are going with the speed of light, sir.
uh, Speed of sound or speed of light? What means? I don't understand.
Today, today you are going very fast, sir.
Yeah, because what's the meaning is I currently running out of charge. At least we do have complete that. Tomorrow we will discuss again on this topic, and meanwhile maybe you can discuss it. What is my priorities? Because if it is switched off in between means um today's your time is also waste, my time is also waste, right? So that's why at least we have completed something, na? So that's why we will discuss it tomorrow again for 15 to 20 minutes on this, and we can continue on the 3 transformer as well. I seriously doesn't know. Today the power cut is continuously happened at 7:30 exactly. It's my bad luck. So I'm so sorry for that.
It's all right, sir.
Yeah. So we will discuss it tomorrow again. Okay, tomorrow again, and we will check it by uh, tomorrow 7:30 sharply, and we can continue off again 2-1 transformer and taking off the 3-1 transformer. Okay.
Yeah, okay, sir.
Thank you.
Great,
See you
thank
tomorrow.
you.